There we go. So with 2D and 3D triangles, if you can keep in mind, right? If I draw like a rough image here, let me do this, do this, do this, and do this. How many triangles do you see here?
4.
There's 4, right? And then if I say that this is like 90 degrees, and then that this is equal to 90 degrees, and then maybe this is equal to 90 degrees. Does that make sense?
Right, it does.
It does. And then do you see that this being 90, this being 90, and this being 90, do you see that it automatically shows you that these are not in the same plane? Yeah, because if it was on a flat surface, then everything would need to add up to 360, right? Yeah. But the moment we see that it is, oh, wait. Snap, why did I do that? Yammer. Let's see, I have to wait for the call to come back. Oh, sorry. I literally closed everything. I closed everything by mistake. But anyways, the point I'm trying to make is that with 2D and 3D triangles, the idea is to be aware of which plane you're working with, you see. So for example, in this shape, right, if I have here labeled A, B, C, and then this point in the middle is D. The triangles that we have is A, B, and C in the front, as you can recall from the course. And then we have C, D, B, which will be on the ground like this. So this would be like B, this would be D, and then this would be C. And then on the left and right, so on the left, we'll have a triangle like this one, where this is like C, D, A, and then same on the right, we're going to have, what's this thing? G, A, and B. Do you mind just muting your mic?
Oh, is it not muted?
Nope.
Is it not muted still?
No, it's not. Just click like the mute button. Like
Oh, I pressed it and it says it's showing that it's muted. I don't understand what is it doing?
Well, if it was muted, I wouldn't be hearing you.
Oh, I think I think it's because I put the loudspeaker here. I think I have to go back to my headphones.
Oh, no. Like, you see, I need to talk on WhatsApp, ne? Just click on the mute. Yeah, it's perfect now. I can't hear you. There, but you can still hear me, you see. So this is fine. If you want to say something, then you can always just unmute your mic. So anyways, so with these 4 triangles, right, the idea is whatever question you will be asked, it's all a matter of working with the side that is relevant, you see. And it's clearly a matter of never overthinking anything. So if I can search for a paper here, right, let me say here, no, so that I maybe get some November papers or something. So here, let me try and find, whoa, goodness, yes. Let's see. Yes, ma'am. Yes, ma'am. So let's see. Let me get 20. It is grade 12, 2015 maths paper 2 only. Yeah. So if we look at this paper, right? If we go to the 3D section, the one thing that we're going to do is we're going to just talk about the question verbally before trying to like answer anything. So when you look at an image like this one, right, before, without even us talking about the description or the questions that they're asking, if you look at the question we have here, you see, even before we start on it, I mean, if you can look nicely, coincidentally, we have something very similar to what we were talking about, almost identical, because you can see here automatically they have given us, I mean, the description, right, says a corner of a rectangular block of wood is cut off and is shown in the diagram below. The inclined plane, that is ACD. So the inclined plane, you see, they're talking about the inclined plane, meaning that it's not on the ground, like it's like slanted. So you have A, C, D. But then before I even keep talking, right? How many triangles do you see in this sketch? Don't forget to unmute yourself. You see 4, right? And then what are those 4 triangles? Okay. Mm-hmm. Yeah. And then which triangle is the half theta in? And then which triangle is the theta in? These 2 thetas. Or this one rather. This one. Yeah. And then this one. Uh-huh. So you can see that wherever each triangle is, wherever each angle is, it's in a specific triangle. You see, so here you can already see it's 2 different triangles that your angles are in. It's not like one angle because they're not in the same plane. So with all that being said, all these dimensions given, they told us these 2 are equal to theta. They told us that this is half theta. I mean, they told us this is x plus 3. It doesn't matter. Now, the thing with 3D and 2D triangles is your questions always need to be worked out based on something that is already pre-existing. For example, here they're saying determine an expression for CAD in terms of theta. So an expression for CAD. CAD is this angle up here. And then we're dealing with this triangle here. So keeping that in mind, what do you think we can do for 1 mark to get that angle in terms of theta? Yeah, everything adds up to 180. So 180 minus 2 theta is what CAD is equal to. So that is simple. With the next one though. Pardon? Where is the other 3? Oh, yeah. Because we have a theta over here and we have a theta over there. See. So with those 2 thetas, we know that they are in the triangle that's in the front. So for 4 marks now, we're given this. We're asked to get this expression. So whenever you need to get an expression from a 3D or 2D triangles, let me even list the possibilities, you see, because they're not like endless. So you're going to either use the cosine rule. You're going to use the cosine, the sine rule. You're either going to use the area rule if they ever speak of area. You're going to either use Pythagoras to help you with something. You're going to use normal trigonometry like so, Katoa. Pardon? Yeah. 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 So the idea is, right, anything you're going to use all goes back down to what its formula looks like. So if you look at, for example, let me put here the math formula sheet, right? If I take out the math formula sheet and we look at what we have. So the other thing is, right, I mean, like right now, if you don't have a formula sheet somewhere close by, you see, it means there's something wrong, because your math formula sheet is something you want to almost use just like a calculator, in the sense that anytime you're working on anything math related, the moment you don't have your formula sheet, you almost have your mind closed up to what you have and what you don't have. So, for example, before we look at what question they're asking here, right? If we have our formula sheet close by, as we always should, what we can already see here is whatever question we're ever going to be asked, right? These three, we know that we'll always use them. We're either going to use two at a time here and all that. But then the idea is with any of these, it's all a matter of asking what do you have and what do you not have. Because if you're going to use the sine rule, any formula that you're going to use always needs you to only be missing one thing. So for you to use the sine rule, you can already see that, okay, I at least need to throw in an angle in there. I need to throw an angle in there. I need to throw a side in there. And then this can be missing. And then it could be all juggled up. You could have this side here, and then another side, and then an angle, and then this is missing. You see, the combinations are not a lot. It's all a matter of what do I not have and what do I actually have. You see, so if you have any three things here and one of them is missing, then you know you can use the sine rule. With the cosine rule, you can already see here, you clearly, just by the way the formula looks, you can see it's more demanding. It's more demanding in the sense that you're only going to use it if you at least have quite a lot of information. Because look, this here, it requires only one angle, right? Which you can see. Or it requires you to be working out one angle. Meaning any formula, you either ask yourself, in this formula, do I have the rest for me to use this formula? Like here, if you're going to use the cosine rule to get an angle, clearly you need 1, 2, 3, all three sides, you see. And then if you're going to work out a specific side, automatically here you know that you will always need at least two sides given and an angle that is going to be in between those two sides. You see, because this is telling you that this side goes with this angle. So your formula always tells you whether you're going to use it or not. You see, like here, if you were going to use the area rule for anything, the first question is, do you even have area given? Or is area even asked? If area is not given or area is not asked, then there's no business here. There's no need to be thinking of this formula at all. But then say area was mentioned somewhere, then we could maybe consider this. Maybe we're given area somewhere and we're given two sides as well, and the angle in between them is missing. Then we can use this formula, because with these formulas, always just think of a generic triangle where you have A, B, C, and then here you have tiny c, tiny b, tiny a. You see, so whatever formula you're going to use, right, for you to like judge if you have enough information, just use this idea. You see, because as we said, if you're going to use the sine rule, this is telling you that you at least need a side and its opposite angle. If you don't have at least this going on at all, then you can never use this. You see, because this here, you can see whatever combination you're going to think of, it always requires you to at least have one angle and its side given. Like you see, if I'm looking for A here, I need this and this and this. If I need to work out the angle B here, right, I need this and this and this. You see, if you need to work out the A down here, you can already see it's the same idea. This and this both need to be given, which is the angle and its opposite side. You see, and then here you also at least need the side which is opposite the angle you're looking for. And we said it all works in this order, right? Where this is the angle, this is the opposite side. And then this is the angle, this is the opposite side. It works for all these formulas. And then for the cosine rule, all it says is that this angle, or rather this angle, right, goes with this length. Meaning in your shape, if you have this angle and this side, you know, then you can either work out this side or this side, depending on if you are given enough information. Because the idea with the formula is it's supposed to work with you. It's supposed to like help you see if you can use it. So let's see. So with that goes for sine, the sine rule, the cosine rule, and the area rule. It all depends on what in the formula do you have and what are you looking for. Because if you have too many things left open in the formula, then you cannot use it. So that's why, for example, the cosine rule, it's not something we use very often, but we do use it quite often sometimes. But it's all a matter of knowing that this one already there is a slot for each and every side. So you at least need two sides given. So it's not a matter of cramming. It's a matter of seeing, okay, in my sketch, what do I have? What do I not have? Depending on which triangle you're going to work with. Because we say you never work with all the triangles together. You work with one triangle at a time. And sometimes you use one piece of information from one triangle to help you to get another piece of information in another triangle. And normally with triangles, what helps you to go from one triangle to the other is the side that there will be that they meet. You see, like here for the bottom triangle and the one in front, they meet at CD. And then for the front triangle and the one on the on the left, this is the line that's joining them, you see. And then obviously, I mean, for the back and for the bottom, DB is what's joining them. And then the two triangles, the one on the left and the one on the right, they both have the line AB over there. So if you see that in one triangle you don't have enough information, always look for the line that will be joining one triangle to the other. So with everything we've said now, right, this specific question for 4 marks, we don't have to struggle with it. We have to ask ourselves, if they're going to ask us to prove this, before we carry on with proving this, right, the other two things here, Pythagoras and trigonometry. Remember, this SOHCAHTOA is referring to opposite over hypotenuse for sine, adjacent over hypotenuse for cos, and then opposite over adjacent for tan. So remember these here, you obviously always want to think of them whenever you're working with right angled triangles. So let's put here right angled triangles, right? Man, come on. Right angled triangles. You see, because the moment you don't keep in mind that you have right angled triangles, then you're going to forget that, wait, Pythagoras could help me somewhere if I ever need it. But obviously, I mean, just with all formulas, if you're going to think of Pythagoras, then just keep in mind that you at least need two sides given, and you need to be looking for the other one. If you're going to think of any of this trigonometry, then you need to remember that all those formulas, they require you to have an angle or looking for an angle when you have been given two sides, you see, or you given two sides and you're looking for an angle, you know, it can vary. But then our point is all formulas are what should help you see if you should use them. So in the question that were asked, right, it's not a matter of like, let's say fishing for a formula first. No, whatever question you're asked, see which triangles have the relevant information that they are talking about. Like for example, if we are looking at here, they're saying we should prove that cos theta is x over x plus 2. I mean, just by looking at the image, we really don't have to look far to see where is theta and which triangle here has x. The one in the front here is bluntly the one that has x and theta. So we want to focus on that one for a bit. Apart from focusing on that one for a bit, it looks like the main one to focus on actually, because the rest almost look a bit useless. Because here we have x plus 3, and then here we have 2x, and then here we have theta, here we have theta, here we have 180 minus 2 theta if we ever need it. Up here there's A, this is D, this is C. So with all this being said, right, in terms of you now coming up with this expression, you have to ask yourself in your image here, right? Do you have, let's say, you want to ask what do you have in this image? So you can already see here you have if let's say you see you're not given like actual numbers, it doesn't matter. This here is good enough as a side given, even though it's like x plus 3. This is also good enough as a side given, even though it's 2x. This is good enough as an angle given. This is good enough as an angle given. And then one way or the other, I mean, like this being 180 minus 2x, it's good enough as an angle given. So with this kind of an image, you literally want to think to yourself of a formula that allows you to incorporate at least something that has x plus 3 in it, which is this side. And then obviously, I mean, like the 2x, I mean, like that's bluntly going to maybe contribute to the x on top. And then obviously we have the thetas here and the 2 theta. It doesn't matter. They are easily going to contribute to the cos theta. So with that being said, right, this is how you choose your formula. Here you can literally ask yourself, okay, fine. I mean, like here, you have a side and its opposite angle. So this can help you if you want to use the sine rule. And then the other thing is, if you wanted to use the sine rule, you also have here an angle and its opposite side. So that's like perfect for the sine rule, because the sine rule is set up in that way. You see, the sine rule is set up in a way that you need to be working with the side and its opposite angle, a side and its opposite angle. And then we can already see here sometimes it may not be a matter of what is missing. It's all a matter of what do you have information for. You see, here we have information. Here you could use, if you were thinking of the cosine rule, you know, the issue now with the cosine rule is you have an angle here, fine. You have one side, another side, fine. So you have two sides, right? But then on the third here, you don't have anything to put in your formula. You see, it's blank. So you would not want to go for the cosine rule. If you're thinking of the area rule, I mean, like, there's no need to think of the area rule because there's no area mentioned in this whole question. If you're thinking of Pythagoras or any of these three, we cannot think of those right now because our triangle here has no right angle, has no right angles. Yeah. Why would you want to use sine? Wait, you're asking in this question, why would we want to use sine if there's a cos over here? No. You mean the cosine rule? Yeah. So here the reason we cannot consider the cosine rule is because if you look at the cosine rule formula, we need to throw something here, something there, something here. In our triangle, we don't have that kind of information. We only have something to put for one side, something to put for another side, and then for the third side, we don't have anything to put in our formula. You see? Because your thing is muted, by the way. Sorry, yeah. So that's the idea behind which formula we use. We always ask, do we have something to throw in everywhere in the formula? Here we don't have something to throw in everywhere. But then in the sine rule, we have something to throw in everywhere. Because we said already, okay, fine. I mean, regardless of the fact that there's a cos here, that's the least of our problems right now. Because now at least we know we can put in this and this. That can work nicely. And then we can put in that angle and this side. That can work nicely because at least it will give us somewhere to start. And the lucky thing with trigonometry is, I mean, you can start with sines, but then you can, you know, because that's just how trigonometry works. So in our sine rule, already we know that we want sine, the side on the top, right, which is 2x, its opposite angle is 180 minus 2 theta. So here we'll have sine 180 minus 2 theta. And then here also, we have here x plus 3 at the top, Just change this thing here. And then here we have theta at the bottom. Do you see it? So with all this being said, we can clearly see that we can easily now just try and simplify our trig expression. Our point here is to not worry about what we're trying to prove. Our point here is to just try and simplify this expression. So simplifying this expression, you can already see that clearly, I mean, like this is where the cos is gonna come from. Because if you look nicely, right, here at the top, we have 2x, we cannot do anything with it. Down here, our reduction formula will tell us this is going to be sine 2x. I mean, sine 2 theta. And then the sine plus the x plus 3, nothing can happen there. Nothing can happen to the sine. And then now we are in trigonometry territory, meaning, I mean, like double angles, compound. Yeah? Pardon? Yeah, it doesn't matter. You can have it, you can have the sides at the bottom and the angles at the top, as long as it matches. So here, if we have sides on top, it's fine. If you have angles at the bottom, it's fine. If you want to have the angles at the top, it's okay. If you want to have the sides at the bottom, it's fine. As long as you see that it's matching. If you're going to have A over sine A, here you need to have B over sine B. And then for the other one, it's the same idea. If you're going to have sine B on top, here you're gonna have B at the bottom. You're gonna have sine A on top, here you're gonna have A at the bottom. You get it? Cool. Yeah. So here now you can see we're not even supposed to be stressing about anything now. It's just a matter of us using trigonometry. Like here at the bottom, anything that cannot be changed, you don't need to worry about changing it. But anything that can be changed, just change it. Because you see here, this is gonna give us 2 sine theta cos theta. This is giving us x plus 3. This is giving us sine theta. Now, because we're dealing with the fraction on the left and the fraction on the right, I mean, you may be thinking to yourself, okay, what can we do here? Well, the fortunate thing is, without maybe overthinking it or without maybe doing anything fancy, we can just cross multiply first. Meaning you're gonna have, when you cross multiply, just make sure that if you have 2 terms at the top, make sure you put them in brackets so that you don't end up messing up. So here, this is what we have. Let me just leave this one for now. And then on the right side, we have 2x times sine theta. You see, of which from here, remember, we already know that we're trying to only have something that has a cos in it. So automatically we can see the signs can go away here. We can divide by sine on the left, divide by sine on the right, and these go away. You see, that's why the brackets are important there, so that we have something that's already factorized. So here now we'll have, actually we can divide by 2 sine theta. Because if you divide by 2 sine theta, the 2 here cancels the 2 here cancels the 2. And then we'll just have x on the left. On the right, we'll have x plus 3 with the cos theta. There we go. So firstly, on the left and the right, what's common is 2 sine theta. You see? So we can divide by 2 sine theta on the left, 2 sine theta on the right. What's going to happen now is that the 2 cancels the 2, the sine theta cancels the sine theta. The 2 sine theta cancels the 2 sine theta. And then we have x on the left. This is equal to x plus 3. And then cos theta. And then here, judging from what they want cos theta to be on its own. So you can just divide both sides by the x plus 3. There we go. You see it? You see. So if you can judge from what we did here, it goes back to what we said in the beginning. Depending on what shape you have, it doesn't matter. We at no point ever considered that this was a 3D shape in whatever we were doing, because whatever question they asked, we just focused on a 2D image, because we cannot work with all of them, even if we wanted, you see. So here we said, this is what we have at your disposal. It's not a matter of cramming it, but you can just keep it in mind. I mean, you could just memorize these 5 things. They are all on our formula sheet anyways, except for the trig ratios, but then the trig ratios are like easy to remember. So as said already, if you yourself right now know that there is no formula sheet like right now somewhere close by, let's say almost like at arm's reach, you see, that's already a problem. Because the same way you probably have your calculator next to you is the same way you want to have a formula sheet. Because a formula sheet is just an extension of the tools that you have so that you stay reminded of what you actually have. So that's one thing I can say up front. Your formula sheet, you want to have it. If it's not printed out, it's fine, but then make sure it's somewhere very close by. If you have like a PDF version of it somewhere where you can always access it, then you want to do that. If you don't have what you may call the formula sheet in PDF format, I can send it right now so that at least, yeah, definitely. Perfect, perfect, perfect. Yes, I will send it. I will send it. So what